Here's a video on section 8.3 on logarithmic functions. So before we talk about logarithmic functions, it's important to talk about properties of exponents. So here we have a to the 0 equals 1. You guys should know that. Also, when you multiply two powers of the same base, here the bases are both a, you would add the exponents. If you move all the way to the right of the first row, you have a to the x over a to the y. So when you divide two powers of the same base, you subtract the exponents, so it's a to the x minus y. And the one right in the middle, when you raise a power to a power, you multiply the exponents. Now, exponents could also be distributive if the two bases are being multiplied or divided in the case of the first or second equations in the second row. But if you have a plus between a and b or minus between a and b, you can't distribute the exponents, otherwise you're violating the order of operations. If you have a negative exponent, put on the bottom. And the last one in the last row is just similar situation. So these should be pretty straightforward. You know, this is 2 to the 5th power, which I know is 32. It's 2 to negative 1 power, which is 1/2. Here you multiply the exponents because you're doing 3 squared 3 times. So it's 3 to the 6, which I believe is 729. That you got to flip, then square, which is 9. This would be 3 to negative 1 power. And this one, because they both have 1/2, you could write 6 to the 1/2 power, or root 6. And by the way, coming back to example 5, that's 1/3. Yeah, because again, you can multiply 2 and 3 together, pull out the 1/2. It's basically the reverse of that distributive property that we see right there in the first equation, the second row in the table above. So why do we do this? Because logarithms are the inverses of exponential functions. So we want to make sure we understand our exponents really well if we're going to work with logarithms. And remember, these two relationships are the same. So you might remember back in the day doing problems like this here. And that's just 3 because 8 equals 2 cubed. And why do we have it in the first place? Because what if you have your exponent as an unknown, and you want to isolate the exponent? We have logs to help us do that. Also remember a common log is base 10. So if we don't see a base, we assume it's base 10. And actually, probably my best to pull up a graphing calculator while I'm at it. We'll come back to it in a sec. So here we're going to rewrite each of these equations into exponential form. So the 49 stays where it is. And you take this space and raise it to the second power. And that, of course, is a true statement. So the input of your log now becomes the output, right? So 64 is my input. It equals 4 cubed. 27 was my input. Now it's my output. We raise 9 to the 3/2 power, which is going to be 27 if you work it out. Because remember, that's root 9, then cubed. 3 cubed, of course, is 27. Now here we go in the reverse. We want to isolate the exponent. So 2 equals log base 525. Half, and that's kind of a funny one, equals log base 12 of 2 root 3. 2 root 3, by the way, is 12 to the 1/2 power. So the base of the power becomes the base of the log. Here, -4 equals log base 3 of 1 over 81. And then here we're going to evaluate. Usually what I like to do is set these equal to x or y or any letter you like. So the 128 stays where it is. 2 to the x. 2 equals 16 to the x. 1 over 27 equals 3 to the x. So x is 6. X is 1/4. X is -3. Because 3 to -3 is 1 over 27, because we got to flip it. 4 through 16 is 2. And if you multiply 2 6 times, you get 128. Very short notes, which is good for a Friday afternoon. Natural logs. If you have log base e of x, it's natural log of x. So whenever the base is e, and e is simply a number that approximates to 2.718. It was devised by some old-time mathematician by the name of Leonhard Euler. And what he discovered is that if you take this expression, 1 plus 1 over x raised to the x power, and let x go towards infinity, it will converge towards that number. And this is a number that's used often in lots of modeling situations in science and in business. So that's why we have it. So here, you have to write this in exponential form. So you could rewrite ln as log base e, x equals e to the 4. Here, log base e10 equals x, 10 equals e to the x. So remember, it's just the same thing as before. We're here, your base is e, so you can isolate x, and it becomes log base e 50, or x equals ln 50. Again, the whole point's to isolate the exponent, so 0.5 equals log base e x, 0.5 equals ln x. And the last bit, something called a logistic growth model. So you want to plug in 8 for t. So t represents time. And what is this model all about? So it's like an exponential model. You see it grows quickly, but then it levels out. It's actually more of a realistic model. For example, say looking at people getting infected with like the flu at Sacred Heart. Say 4 people in our class have the flu, and they don't call in sick, so then they get everyone else in the class sick, and then we go to other class and we get them sick. All of a sudden, the spread of infection increases exponentially, right? But at a certain point, we have to reach a limiting value because there's only so many people on our campus. It's not going to just keep going up like that. Kind of same thing with COVID about 3 or 4 years ago when people were getting COVID. It was increasing very quickly, then it would have flattened out eventually. So logistic model is a more realistic model we use for things growing, but then eventually leveling off. C is what we call the carrying capacity or limiting value. Like, for example, if you're looking at number of people getting infected at Sacred Heart, or just looking at the students, not the adults, I believe we have 650 students, so C would be like 650. A and B are constants that depend on the situation you're dealing with, and you have to solve for those separately, but we're not going to worry about that. What we're just going to do is just plug into this model here, which involves E as well. So you simply plug in 8 for T. And use a calculator to work it out. And look, it looks like this is the weight in grams of a bacteria growing. So I probably work out the denominator separately because there's a lot of stuff going on here. And second ln is where you look at E, negative 0.5 times 8. And I'm going to do 1.26 divided by that number. Hit second negative to call that up. So it's actually pretty close to limiting capacity. 1.25. Actually, we'll do 1.254. So pretty simple. Just want to make sure you guys are exposed to what a logistic model looks like. Involves E, and I think we are, and you can also do a logistic model without E as the base there, but that's fine. We'll just use this one here. And that concludes the notes.